Good morning, everyone. Welcome to this new appointment of the 40 under 40 lecture series on combustion. Today, this morning or this evening for our speaker, we have the pleasure to have Dr. Xiaoyuan Zhang, who is currently a researcher at the University of Science and Technology of China. She received her PhD degree from Shanghai Jiaotong University in 2019. And during her doctoral studies, she served as a joint PhD student at the CNRS, Orléans, in France. Following her graduation, she held a position as a postdoc fellow at the Clean Combustion Research Center at KAUST, and her primary research interests encompass combustion chemistry, modeling of real fuel combustion, alternative fuels, turquoise, hydrogen, and related areas. Dr. Zhang has authored approximately 50 papers with over 1,500 citations and H index of 20. And she was honored with the Bernard Lewis Fellowship during the 38th Symposium on Combustion. Xiaoyuan, thank you very much for accepting our invitation, and I leave you the virtual floor. Thank you.
Thank you, Professor. It's my great honor to have this chance to share my work with you. So I would express my gratitude to the Belgian section of the Combustion Institute. Today, my topic is on modeling real fuel combustion chemistry, and I will address this point from both ends. First of all is the real fuel pyrolysis, and the other is for fundamental fuel oxidation. This figure presents the petroleum distillation process. We know that petroleum itself is a complex mixture, and its distillation products like gasoline, kerosene, and diesel oils are all complex mixtures. If we compare their major components, we will find that although their molecular weights are different, their chemical classes involved in these conventional transport fuels are very similar, which can be divided into normal alkenes, isoalkenes, cycloalkenes, and aromatics. Current primary motivation of a kinetic model is to predict a real fuel combustion chemistry. For example, it's ignition delay or pollutant formation and so on. However, the transport fuels are all complex mixtures, posing a great challenge to model their combustion chemistry. A kinetic model can be used to describe the combustion chemistry, and it mainly has two purposes. The first one is for fundamental understanding. This requires a model should be detailed enough so it can reveal how the fuel decomposes to some key intermediates and how the intermediates influences the heat release and the pollutant formation. So this probably results in an increasing in model size. Well, its another purpose is for practical applications. This figure shows that the CPU time increases with the increasing number of species in the kinetic model. While for practical CFD simulations, we need a model that is compact enough. So these two purposes seem to motivate the kinetic model development towards two opposite directions. So what we are thinking is how to balance these two purposes. Well, this requires a deeper understanding for the combustion process and also some novel approaches to model real fuel combustion. Under high temperature conditions, typically 1000 K, the combustion can be divided into two stages. The first stage is the fragmentation of real fuels. This is a very fast process. In this process, fuel decomposes to some key pyrolysis products, as we can see here. And the second stage is the oxidation of these species. This is a slow and rate-limiting process, determining the critical combustion parameters. In this presentation, I will address both of the two stages. In the first part, I will introduce a functional group-based approach to modeling the real fuel pyrolysis process. And in the second part, I will introduce a C1 to C2 co-reaction mechanism, which is used to describe the oxidation of fundamental fuels. Okay, let's first look at the first part. This slide compared the different modeling approaches for real fuels, detailed model methodology, decoupling methodology, and high-chem methodology. Compared with the detailed method, lumped reactions are involved in the decoupling and high-chem methodologies. So the model size are much smaller than that in detailed model. The size of the boxes represent the size of the model. However, since the model parameters in the lumped model in these two methods are obtained based on fitting the experimental data, so it is not an it is not a predictive method as predictive as those in for detailed model, because in detailed model we obtain these model parameters from ab initio calculations or rate rules. So in this work, we are also thinking about the high-chem model methodology. In this model, if you change the feeds of the real fuels, you may need new experimental data to derive the model parameters. So in this work, we are thinking of combining the advantages between the detailed and the high-chem model approach, which make the model has a compact size, and also can account for real fuel variability and is fully predictive without fitting the experimental data. So in this work, we proposed a functional group-based approach to model real fuel combustion. The philosophy of the model is also developed based on decoupling methodology. We also use a lumped mechanism to describe the fuel pyrolysis process, and also a detailed model and a detailed base model to describe the oxidation of the key pyrolysis products. We know that the model parameters, like the stoichiometric parameters of lumped reactions, thermodynamic data, kinetic data, are all closely related to the fuel structures. So in this work, we hypothesize that these model parameters are only dependent on the functional groups present in a fuel mixtures. The functional groups distributions can be easily obtained by NMR or GC-mass experiments. So we can use the functional group information to estimate the thermodynamic data and the transport data according to Benson group additivity method and the Joubek method. And we can also estimate the kinetic rate constant based on the rate rules developed for pure fuels. For the stoichiometric parameters of the lumped reactions, we can use the machine learning method to correlate their relationship to the functional groups. Specific speaking, I would take CMHNOZ as an example. It is a fuel. It represents a real fuel mixture. MNZ can be obtained from the experiments. R1 represent an unimolecular decomposition reaction. It connects the fuel molecules and the key pyrolysis products, which can be divided into several groups. The first group is for alkenes with one double bond. Second group is for the compounds with multiple double bond. The third group is oxygenated species. If you consider hydrocarbon real fuel mixtures, QD should be 0. And the last part is for radicals. Lambda 3, lambda 4, which are highlighted with red color, are stoichiometric parameters. Their definition are shown here. They are closely related to the yield of key pyrolysis products. Okay, right now, if we know the MNZ values from the experiments and then obtain the stoichiometric parameters from machine learning methods, which will be introduced later, we can compute ED, BD, QD based on CHO element conservation. Similarly, we also consider other reaction classes. R2 to R7 are H abstraction reaction classes, while R8 is H addition elimination reaction class. While this is an optional reaction class, when there is when there are considerable alkene groups, we need to consider R8. Well, for thermodynamic data, we can add up the contributions of each functional groups to compute the thermodynamic data of the real fields. For kinetic data, we can adopt the rate rules developed for pure fields and add up the contributions of each CC bond dissociation reactions and each CH bond dissociation abstraction reactions. So right now, the only unknown parameters are the stoichiometric parameters, which are closely related to the yield of key pyrolysis products like ethylene and propene. In this work, to get the yield of key pyrolysis product, we adopted the machine learning method. First of all, we construct a database consisting of the yield of a key pyrolysis product in a lumped model for pure fields. H abstraction reaction, isomerization reaction, and the decomposition reactions are lumped into one reactions based on the time scale analysis. This is an example for normal hexene. Lumped models for 50 pure fields were developed based on timescale analysis, including normal isocycloalkanes and aromatics, and their distributions are shown here. These the yield of a key pyrolysis product shown here as red colors numbers are weakly dependent on pressure and the temperatures, and they can derive from the equilibrium yield of free radicals. Similarly, we can develop we developed the lumped kinetic models for 52 pure film fields and obtained the yield of key pyrolysis products shown here. And this is a distribution of different film fields. To verify the reliability of this yield of key pyrolysis products, we validated the lumped model against the literature data, and this work has already been published right now. Well, with the reliable key pyrolysis product for pure fields, and we know the functional groups present in a pure fields, we can adopt the multiple linear regression to derive the coefficients of B0 to B10. This means that once we get this B0 to B10 for a given field mixture, we know their functional groups. Then we can use B0 to B10 to calculate the yield of a key pyrolysis product, and then to calculate the stoichiometric parameters. This figure presents the actual yield of a key pyrolysis product and the predicted values based on the equation. As we can see, good agreements can be achieved. Similarly, for real biodiesel fuels, we adopted different kinds of functional groups. For example, we considered the alkene groups for correlations. Similarly, we can obtain B0 to B8 from the correlations. So for a real biodiesel mixture, if we know its functional group information, we can use B0 to B8 to compute the yield of a key pyrolysis product and then to compute the stoichiometric parameters. And this figure also presents the predicted yield of a key pyrolysis product by B0 by this equation and the actual values. As we can see, good linear relationship is achieved. Okay, by far, we obtained all the model parameters in the FGMAC approach. So we, in order to test the reliability of this model approach, we constructed the kinetic models for gasoline, jet, and rocket fuels and biodiesel fuels based on FGMAC approach and tested the experimental data available in literature. Here are the tables here showing the validation conditions, as we can see, including both global and speciation data. Right now, I will give you some examples for the validation results. This slide presents the ignition delay time for gasoline fuels. Symbols are experimental data. Solid line represents the present FGMAC plus Aramco base model. Dotted line represents the present FGMAC plus USC-MAC2 model. Note that the only difference in these two models are the base model. The same fuel model are adopted. As we can see at the lower temperatures, the solid line FGMAC Aramco model can better predict the results, the experimental results, while at higher temperatures, the FGMAC USC model can better predict the ignition delay time. This reveals that the accuracy of the base model largely influences the accuracy of this model approach. So in the second part of my presentation, I will introduce the efforts on the base model development. Well, this is for the validation results against the jet and the rocket fuel targets. The figure on the left-hand side are the pyrolysis speciation data measured in rocket fuel, and the figure on the right-hand side are the laminar flame speed validations. As we can see, both solid and dotted lines can reasonably predict the experimental data. Well, we also validated the biodiesel FGMAC model. This is for rapeseed oil this is for the pyrolysis data in a flow reactor, and this is the rapeseed oil oxidation in a GSR. Solid line represents the present FGMAC model, and dashed line represents the detailed model from literature. As we can see, the present model can better predict the experimental data. Okay, in this section, we proposed a new functional group-based approach to model real fuel combustion chemistry. And this approach is aiming at constructing the relationship between the functional groups and model parameters. No experimental data are required to fit any of the model parameters. To test the reliability, we developed the kinetic models for both fossil and biodiesel mixtures based on this approach, and validated these models against the literature experimental data. The results show that the FGMAC approach is capable of modeling real fossil and real biodiesel fuel combustion. Well, my second part is on the co-reaction mechanism, and it will be used to describe the oxidation of the fundamental fuels. Okay, here I only focused on the C1 to C2 reaction mechanism. As I introduced before, the fragmentation of the real fuel is a faster process. take normal dodecane as an example. At the very early 20 microseconds, the fuel has already been pyrolysis, and the fragments like ethylene was produced. Well, the oxidation or conservation of ethylene is a slow process. When it is consumed, the ignition occurs. So these small species plays an important role in determining the critical combustion parameters such as ignition and so on. Besides, from a fuel aspect, syngas, natural gas, and small alcohols all belong to the C12C2 reaction mechanism, and they are also the base mechanism for large and real fuel development. Well, you may think there is no space for studying the core reaction mechanism because it is already accurate enough. However, this is the roadmap for mechanism development. We can see the reaction pathways and accurate rate constant are the sources for model development. Recently, new reaction pathways like chemically thermomolecular reactions and more accurate rate constants were available in literature, providing opportunities to get more reliable sources for model development. In addition, high pressure measurements for global and speciation data are available, which can be used to further validate and optimize the core reaction mechanism. However, if you plot the size of a data set for C1 to C2 fuels, you may find that there are still limited data for oxygenated fuels, such as formaldehyde, ketene, and acetaldehyde. And although there are enough data for methane and ethane oxidation, the structure information of them, especially at low temperatures, are still limited. Besides, we still have limited understanding of small radical growth chemistry, although they are very important for PAH and soot formation. We also have limited understandings for HO2 and RO2 reactions, although they are very important in determining low temperature chemistry. These figures shows that there are still large discrepancies for these HO2 and RO2 related reactions. So in this work, we would like to compute the rate constants of RO2 related reactions to provide more accurate sources for model development. And then we are also aiming at obtaining the validation data for oxygenated fuels and extending previous conditions to wider conditions, and also developing an ongoing mechanism focusing on the pollutant formation and low temperature chemistry. This is the hierarchy structure of the present base model. First of all, we will focus on the pyrolysis mechanism of methyl radicals, and then we will focus on the base mechanism of CO, CH2O, and methyl mechanism. Thirdly, we will focus on the sub-mechanisms of acetaldehyde and propanol, focusing on the low temperature chemistry of methyl and ethyl radicals. Well, the theoretical calculation methods were adopted in this work, including the ionization energy calculation, potential energy surface calculation, and rate constant calculation. Different methods and its corresponding uncertainties are shown in this slide. For experimental methods, we adopted various experimental methods. First of all is the synchrotron-based VUV photoionization mass spectrometry. We use this diagnostic method to detect the speciation data measured in an atmospheric GSR, a premixed flame, and flow reactor experiments at various pressure. The uncertainty of this diagnostic method mainly results from the uncertainties of a photoionization cross-section. Since the photoionization cross-section has uncertainties ranging from 25% to a factor of 2. So this is the main. This is a this is corresponds to the uncertainties of this diagnostic method. Well, we also use GC mass and GC method to diagnose the speciation data measured in a high pressure GSR. The uncertainties of a GC is smaller. It's much smaller, around 15%. Well, we also use a combustion vessel to measure the laminar flame speed. The slurring method was used to record the flame propagation. For model development, we firstly construct a database for model validation. Only high-quality experimental data with clear error bars were considered in this work, and comprehensive experimental conditions are collected, which can cover wide temperature, pressure, and equivalence ratio conditions, and various type of data, including global and speciation data, are involved. For the rate constants, we evaluated the sources of the rate constants and estimated the uncertainties of the rate constants for model development. No adjustments were attempted to match the experimental data. The kinetic model was also validated against the comprehensive experimental conditions. To reduce the model stiffness, we exclude some minor reaction channels when constructing the model. Well, let's first look at the first section. It is related to methyl pyrolysis, methyl-related growth chemistry. In this part, we are aiming at providing new validation data under intermediate temperature and various pressures, and developing the methyl-related growth chemistry to review the pressure dependencies of a pollutant formation. So in this work, we didn't adopt the methane as the target fuel, since the CH bond is too high to break. Instead, we adopted the diacetyl as a target fuel due to the much weaker CC bond. As we can see, the chain initiation reaction in diacetyl would be much easily to occur compared with the methane radical. So diacetyl would be a much more efficient methyl precursor. In this work, we conducted the pyrolysis of diacetyl in a flow reactor and also in a GSR covering various pressures. Compared with previous experimental conditions in this work, we extended previous operation conditions to lower temperatures and wider pressures. For model development, we considered about the C1 plus C1, C1 plus C2, C1 plus C3 reactions, and also considered about the sub-mechanisms of C4 and benzene formation. In order to better account for the pressure dependencies, the recent progress in calculating the potential energy surfaces of C3 and C4 compounds were incorporated in the model, and rate constants of different branching fractions with their pressure dependencies were considered in the model. Here are the model performance. As we can see, solid lines are the predictions by the present model, and dashed lines are from a literature model. As we can see, the present model can reasonably and better predict the experimental data. So based on the present model, we can use it to review the pressure dependencies of a methyl group chemistry. At low pressures, we found that these addition-elimination reactions dominate the methyl-related groups. It means that the experimental data conducted at low pressures can provide more validation data for these addition-elimination reactions, while at high pressures, the combination reaction dominated the methyl group chemistry. And the experimental data obtained at 10 bar can also extend the previous validation conditions. For the pressure dependencies of benzene formation, we found that at low pressures, mainly the C3H3 propargyl radical combination reaction pathways are dominant, while at high pressures, other reaction pathways become competitive. For example, the H abstraction reactions by phenyl radicals and the combination reactions between C2 and C4 species, as well as the fulvene isomerization reactions. Okay, this is the reaction mechanism for methyl group pyrolysis mechanism. The next section, I will talk about the base mechanism for COCH2 and the methanol mechanism. In this section, we are aiming at providing the experimental data for this base model and developed their kinetic model, focusing on the combustion kinetics of methanol flame at fuel-rich condition. In this section, we contributed the experiments for methanol, laminar flame speed measurements and laminar premixed flame speciation experiments were conducted. For the kinetic model construction, the base hydrogen model is adopted from a Hashmi model, and we incorporated the recently progress in chemically thermomolecular reactions. As we can see, by adding these reactions, the model predictions can be lowered down and can better predict the experimental data. Besides, we also incorporated the prompt dissociation pathways of HCO. And these reaction pathways can increase the predictions of laminar flame speed and better predict the experimental data. In our speciation measurements of methanol, we found that formic acid is an important product. So we also added the sub-mechanism of formic acid to predict the formation of formic acid. As we can see, the present model can reasonably predict the experimental data. Based on model analysis, we found that in laminar flame speed experiments of methanol, formaldehyde is the major components, is the major products, and its related reactions present large sensitivity under various conditions. So the laminar flame speed data of methanol can provide validation data for CO and the CH2O mechanism. Well, this figure presents the comparison between the previous measured and the predictions by the present and the literature models. For the laminar flame speed, at fuel-rich conditions, large discrepancies can be obtained from different models. As we can see, only the solid line, the present model, and dotted line San Diego model can well predict the experimental data. Well, in this work, we extended the equivalence ratio conditions to ultra-rich conditions. Here is 1.5, and we extended it to a 2 and 2.0 and 2.1. As we can see, not only the present model can predict the experimental data reasonably, even San Diego model presents some discrepancies when predicting the experimental data under ultra-rich conditions. Then we analyzed the combustion chemistry under ultra-rich conditions. We found that the temperature is not high enough under these conditions. Let's see, only 1,700 K for the temperatures, much lower than that under fueling and stoichiometric parameter conditions. So the chain branching reaction of H plus O2, its contribution is lowered, while the contribution of HO2 and H2O2 decomposition becomes competitive. So when we perform the sensitivity analysis, we also found that under ultra-rich conditions, the HO2 related reactions become more sensitive and important. So the experimental data obtained under ultra-rich conditions can provide valuable validation data to constrain the HO2 related reactions. Well, for the laminar premixed flat flame of methanol, to conduct the experiments, we upgraded our previous apparatus. We use a single-stage sampling design to better detect the reactive species. This is the fuel radical in methanol. Based on the upgraded apparatus, we can easily identify them. This is the quantification results for C1 species in methanol flame. All these speciation data are related to this reaction. As we can see, I listed the major reactions for the formation of methyl, formic acid, and formaldehyde. As we can see, the rate constants for R141 has a very large discrepancies, while the speciation data measured in this work can provide some constraints for these reactions. Okay. The last section, I will focus on the submechanism of acetaldehyde and propanol in order to study the low temperature chemistry of methyl and ethyl radicals. In this part, we have provided the speciation data for the low temperature chemistry development of acetaldehyde, propanol, methyl, and ethyl radicals, and also developed the submechanisms for these two aldehydes. Based on the model, we also investigated the contributions of the chain branching reactions in these two aldehydes. The GSR experiments at 1 ATM were conducted. The diagnostic methods are synchrotron-based VUV light, photoionization mass spectrometry. Equivalence ratio conditions cover both fuel-lean and fuel-rich conditions. For model development, since there are large uncertainties in RO-related reactions in this work, we computed the H abstraction reactions related to RO2 reactions. As we can see, this figure shows the computed results, red solid line, and the other sources from kinetic models and experiments. As we can see, there are large discrepancies among the present and the previous rate constants, and our present theoretical calculation results can better match the experimental data. For the construction of a propanol model mechanism, the analogy method were used. Now let's look at the experimental results for acetaldehyde oxidation. The figure on the left-hand side presents the identification results. In our work, we not only measured the we not only identified the methyl hydroperoxide in acetaldehyde oxidation. We also measured its radical, methyl proxy radical. Then we quantified our experimental data, as we can see in the right-hand side. The solid line represents the present model predictions. As we can see, the present model can better predict the experimental data. Based on the model, we analyzed the contributions of different chain branching reactions in acetaldehyde oxidation. Under few Lin conditions, when temperature is lower than 600 K, we found that the acetyl radical pathway B dominate the chain branching, while when temperature increases between 600 to 750 K, the methyl radical pathway C become competitive, and this can be confirmed from the sensitivity analysis. While in contrary, under few rich conditions, only the reaction pathway C, methyl-related pathway, contribute to the chain branching reactions. So, under few rich condition, the measured speciation data highlighted here with red color are very helpful to constrain the low temperature chemistry of a methyl radical. As we can see in the sensitive analysis results, the methyl-related reactions are very sensitive to these key intermediates. While similarly in propanol oxidation experiments, we can also measure the alkyl-related species and the fuel-related species. Under fuel-rich conditions, the alkyl-related species dominated the chain branching. So, the experimental data of propanol oxidation can also provide the experimental data for ethyl oxidation. This slide presents the model validation results against the literature data. These figures are ignition delay time measured in RCM, and these figures on the left-hand side are the speciation data measured in a high-pressure flow reactor. As we can see, the present model can reasonably predict these experimental data. And this slide presents the model validation against the experimental data of ethane. And the experimental data are also from literatures. This is for RCM ignition delay data, and this is for the flow reactor oxidation data at 100 bar. Okay, in summary, in this section, we firstly developed the methyl-related growth chemistry. We adopted the diacetyl as a methyl precursor to to obtain the experimental data at intermediate temperatures and various pressures. In this part, we developed a method-related growth mechanism and use it to review the pressure dependencies of benzene formation. Well, in the second section, we focused on the COCH2O and the methanol base mechanism. We found that HO2 radical dominates the radical pool of methanol combustion under very rich conditions, and its related reactions present large sensitivity. So these data can be used to constrain the reactions related to HO2 radicals. In the last section, we focused on the sub-mechanisms of acetaldehyde and propanol. In these sections, we identified different chain branching reactions in the low temperature oxidation of acetaldehyde and propanol. And we found that under fuel-rich conditions, these two fuels can be considered as efficient precursors of methyl and ethyl radical respectively. So the experimental data obtained under fuel-rich conditions can also provide the validation data for the low temperature oxidation of methyl and ethyl radicals. Okay, for future work, for the first part, FGMAC development, what we are doing is to extend its application to model low temperature oxidation chemistry of real fuels. We have already developed an automatic lumped model generation software based on Mamox++. And then we are now using it to construct the database for investigating the low temperature oxidation chemistry. Well, for the second part, the base fundamental fuel mechanism, what we are doing is to extend the C1 to C2 mechanism to C3 to C6 species. A C3 to C6 reduced model will be constructed based on the detailed C1 to C2 mechanism. And also the model uncertainty analysis will be performed to further optimize the base model. Okay, I will show my gratitude to Professor Yuyang Li, Professor Fei Qi at SJTU, Shanghai Jiao Tong University, and Professor Philip Dagao at CRS Orléans, and Professor Mani Sarathi at KAUST. With their collaborations, I can conduct the various experiments and also some modeling work. Okay. Thanks for your attention. I will be glad to take any of your questions. Thank you.
Thank you. Thank you very much for your talk, Xiaoyuan. Now the floor is open for questions. If there are any from the audience, yep, raise your hands or just connect or yeah, let me know. I don't know. Are there any questions? Okay, maybe I will start with okay. I see Alessandro Stagni has a question. Please, Alessandro, go ahead.
Yes, 1 second. Should be visible right now. Okay. Yeah, thank you for your comprehensive and very nice presentation. I just have a question. It's more of a numerical one, actually. You talked about in about half of your presentation on stiffness reduction that you removed some specific reaction to reduce the stiffness of the system. Was there a criterion to do that?
Oh, this is a very good question. You mean the stiffness of the model, right?
Mm-hmm.
Yes, because when we consider about a theoretical calculation results, they will give you the branching fractions for each branching reactions. For example, it will be have a reaction pathway A and reaction pathway B and reaction pathway C. And I only considered the dominant reaction pathways. The criteria is that if the reaction pathways only have 10% along the wide temperature and pressure conditions, and I will directly remove these reaction pathways when constructing the model.
Okay, good. And another question. You do, in the first part, you show your framework for model development through some lumping. My question is, how far can we go in terms of number of species if we consider this lumped mechanism? I mean, I guess that for using downstream mechanism reduction will be always needed. But in terms of species of a surrogate fuel, how many, which is the order of magnitude?
I'm not quite understand your question. You mean the lumping? The extent of lumping?
No, I mean, you said that you developed a mechanism for surrogate fuels that you validated later downstream. What's the size in terms of order of magnitude of species of the surrogate mechanism that you developed? How many species do we have? More or less?
Oh, no. Okay, you mean surrogate fuels? Actually, we are aiming at for the real fuel mixtures. For surrogate
Yeah.
fuel, yeah. Right now we only have for high temperature conditions, we only have the fuel itself. It is the only molecule for fuel submechanisms. If we consider about the low temperature chemistry, then we will consider about the fuel radicals. Only one fuel radical and only one ROO radical and only one QOOH and maybe 10 of species in the lumped mechanism. But right now, for high temperature chemistry, only have one species. It is the fuel.
Okay. Good. Thank you very much.
Thank you.
Thank you, Alessandro. Are there any other questions from the audience? If not, I have a question, a general one. You mentioned about the machine learning techniques, and what's your vision about it, about the use of machine learning for these for kinetic modeling of real fuel? It will be like useful also for scientific discovery to discover some reactions or some mechanism that that were overlooked, or do you think it will be more useful for just for reduction of mechanism or optimization of rate constant and so on?
Okay. We adopted the machine learning method just because we think the first reason is we think that the model parameters itself is related to the fuel structures, and then we would like to find a technique to construct the relationship, directly construct the relationship. So if we have the relationship, we can directly obtain the model parameters from the field structures. This is what we have done. Also, in some previous work or many other researchers' work, they use this technique to directly obtain the predictions. For example, they directly correlated the relationship between the structures and the flame speeds or other ignition delay time, these combustion parameters. And this also will be a good application. But in our approach, we can directly get the model parameters. With model parameters, you have the model. You have the model. You can predict any of the experimental data you are interested in. So if you use the technique to just predict one of kinds of experimental data, you can only use it to predict this certain experimental data. So that's why we use the machine learning method to construct the relationship between the functional groups and the model parameters. Of course, machine learning method can also be used for model reduction. This is also I think it is also promising. Maybe we will, maybe if we have some chances, we can also try this technique and apply it to the model reduction. Right now, we only use it for model construction.
And which technique did you use specifically for to model this relationship in neural network? Or I missed it. I don't know if you mentioned it.
Sorry, can you repeat your question?
No, I was just was curious about if you said and I missed it about what technique did you use? What machine learning did you use? I don't know, neural network.
Yeah. Yes. You don't miss it. I just yes. I use the multiple linear regression, the simplest machine learning method to get the relationship. Of course, we can use more advanced method to get more. Get more results, mean more agreements. But we didn't do that because a very simple method technique has its own advantage. It's easy to incorporate it into model development, and it is also friendly to users.
Okay, thank you. I see that we have another question. Please, Hong Kwan. I hope I said your name correctly.
Hello. Thank you for nice talk. So I have one question about the validation of the model in the subgroup. Yes.
Yes. You mean the validation in the subgroup?
Yeah, I see very good prediction. So I have a question. Do you use the Kemkin for modeling, Kemkin software for modeling, or another software?
I use Kemkin, mainly use Kemkin for simulation.
Okay, so did you introduce heat loss in your modeling?
No, because you see that the experimental targets are mainly high temperature.
Yeah.
I mean, in first part, I didn't use heat loss because my first part mainly focused on the combustion conditions. The ignition delay time is shorter, mainly shorter than 1 millisecond. So I didn't consider the heat loss. But in my second part of a presentation, I did consider about the heat release.
Because so how to estimate heat release by experimental or to put the value around the value to fit the data.
Yeah, some papers will say they're will tell you how they incorporated the heat release. For example, they give how to say, they give a heat loss by a dp dp dt. That means that you can consider the pressure changes for heat loss.
how I cannot understand how you can transfer from dp per dt by heat loss. That's my question. Okay, thank you.
Okay, I think this is a professional question for experimentalist for the
Okay,
shock tube.
okay, good, thank you. And you can explain me the rocket fuel. What is it? You use the surrogate for rocket fuel or real fuel?
For rocket fuel, they are rocket fuel. It's real fuel, not for surrogate fuel. The experimental data are available from Haiwang's work. I think I adopted their experimental data.
Okay, good. And the last question about the laminar burning velocity. Yes. So you talk the mechanism validate for high pressure. So I see just only 5 atm. So did you have another experimental around 10 atm or higher?
Yeah, no higher than 10, but we have the experimental data at 10 atm.
So
But
I
it is
didn't see in the presentation.
yes, I didn't show it. Show the experimental data higher than 5 atm. Yes,
Yeah.
we have the experimental data as high as 10 atm.
Yes. Okay. So last question. Could you explain, please, how you can do the analyze the sensibility analysis for the LBV, laminar burning velocity? The method that you use with Chemkin or another software tool.
Analyze what laminar flame speed?
Analyze the sensibility analysis of methane laminar burning velocity. Yes. At 100
Yes.
atm, yes, and 423 Kelvin. So I don't understand the method that you can analyze.
Let me find this slide for you.
Yes,
Okay.
like the method breed for the shock tube or not?
Let's first look at the
Yes, this one.
maybe this one.
Yeah, this one. So the method that you can, I think very interesting.
Okay. This means that this sensitivity analysis were conducted for this temperature and pressure and various equivalence ratio conditions. We can see the black one is the results for ultra rich conditions. Let's take one example. For example, this one. The sensitivity results shows that this reaction is more sensitive under ultra rich condition compared with other conditions. And similarly, this this is another reaction and this is another reaction. So based on the sensitivity analysis results, we found that under ultra rich conditions, the HO2 related reactions become more important compared with other conditions. This is this is my point I want to express.
And here,
and on the left hand side, I just explain why HO2 reactions become important under ultra rich conditions.
And here you use the method like the brute force. You know, brute force for shock tube, it's the same method to do the sensitivity analysis. You change, you multiply the race constant of reaction by factor 2, 3, and something like this to do the sensitivity analysis. I don't know clear for you. Clear.
The sensitivity analysis was also based on I think it is based on ChemKing Pro, and it is just change the rate constant by a factor of 2, multiply by a factor 2, and divided by factor.
Yes,
yeah.
That's my question. Thank you. So
thank you very much.
Thank you.
Okay, thank you. I think we can close the Q&A session, which was very useful. And also, I'd like to now to thank the speaker also for a nice talk. and for being so available to this Q&A. And yes, so thank you again, Taiwan, for your talk.
Thank you, Professor. Thank you very much.
And I wish
Bye-bye.
you a nice weekend and nice weekend everyone, and have a good rest of the day. And I hope to see you at the next appointment of this lecture series. Thank you.
Yeah. Thank you, Professor. Bye-bye.
Bye bye.
Bye-bye.
Have a nice weekend. Bye bye.